also we have discussed about the ith operator and the equation, the main equation of the complex number, and also we discussed about some operations with between two complex numbers, including addition, subtraction, product, and the division. And also and we discussed some questions as well. And also we did two more theory parts. What was we discussed about the equal of two complex numbers, and also we discussed how should be the complex number getting zero. So on that, the complex number, if the complex number is equal to the zero, then the real part and the imaginary part both should be equal to the zero, right? Now I'm going to introduce another theory part, which is a conjugate of a complex number. So you can assume z, like x plus iy, x and y are both real numbers. The conjugate of a complex number means, so the symbol is z bar. The symbol is z bar. So the z bar means the conjugate. This is the main complex number. This is the conjugate complex number. Conjugate complex number means x minus iy. So what happened here? The positive sign has been changed to the minus. And if it is minus, then it will become positive. But whatever the operation, you have to change the sign of the imaginary part. The imaginary part, the sign should be changed, but nothing changed with the real part. This is just about only the imaginary part. So the imaginary part, the sign has been changed, plus changed to the minus. Therefore, this is the conjugate of the complex number z. The conjugate complex number. Conjugate complex number. So this is the main complex number. This is the conjugate of the complex number. First thing is you have to understand what is the conjugate complex number, and also we have few theories. Okay, the next important thing is the symbol of the conjugate complex number. If you have a complex number z which is 2 plus 3i, then z bar will be 2 plus 3i to the power to the bar, and the bar means only the imaginary part sign has been changed. It's 2 minus 3i. So this is the z bar and the conjugate complex number, right? Then and we have few theorems to be understand with associate with the conjugate complex number. The first theorem is the double z bar. So the double z bar is again z, and the second one is z1 plus z2, the conjugate, the complete conjugate equal z1 z2 individually. The main conjugate is equal to the individual conjugates. Then third one also, here is a minus, also same. The negative operation also same, and also the product as z, which is z1 and z2, z1 into z2, and the fourth one z1 over z2 whole thing bar equal to z1 bar z2 bar. And also the fifth one, z and z bar is surely greater than or equal to the 0. Z and Z bar. The Z bar means the own conjugate of the Z. Then it should be more than 0. Sometimes it can be 0. I will tell you what are the locations, what are the places that they given that this value gives 0. And yeah, these are the things. Okay, one by one I'm going to through the previous theorem. So the first one is Z double bar equal to the Z. So if it double Z mean, so I assume Z as x plus iy, then Z bar will be x minus iy. So it means Z bar will be x plus I minus y. So Z again bar mean that minus I, the sign is again changed, I minus y. So it's x plus iy. So this is actually our Z. Therefore Z double bar equal to the normal complex number. So this is the first theorem that we had. Okay, the second theorem is Z1 plus Z2 whole the complete bar, which is equal to Z1 bar plus Z2 bar. So I am going to start from left hand side. Z1 plus Z2 bar. So I assume Z1 as x1 plus iy1, Z2 as x2 plus iy2. Therefore the addition is x1 plus x2 plus iy1 plus y2. So the bar means the sign should be changed, the imagination part, x2, here it's minus I y1 plus y2. So then we can simplify the bracket, then it will be x1 minus iy1, x2 minus iy2. So this is actually the conjugate of the Z1, and also this is the conjugate of the Z2. Therefore, you can see the theorem number 2 has been proved. So the same thing I'm just suggesting you to do the negative one as well. You can fail it. The property is not the same. The property will be same. Okay. So the next theory, the third one, Z1 Z2 the product, the bar will be equal to the individually product of the conjugates. So then I'm just starting from left hand side. Z1 Z2 bar, Z1 into Z2 bar. So I think so we did this one on our first tutorial. So I think you have remember the value. So now you can see the previous one. So this is the Z1 into Z2. So we did it, the product. Actually we operate it. So now I am directly using the previous result, but I'm not suggesting you to write it directly. You have to simplify it, right? In this occasion I am going to write it because we did it. So this is the property of Z1 into Z2. Actually it's bar is already here. So once you put bar, then what will happen, the sign should be changed. The sign is changed into the minus. So x1 x2 minus y1 y2 minus I x1 y2 plus y1 x2. So here, so after that I'm going to solve the bracket, x1 x2 minus y1 y2 minus I x1 y2 minus I y1 x2. So here I'm again putting I square for here. Minus mean I squared, no? Then I'm just going to put in x1 x2, here it's I squared y1 y2 minus I x1 y2 I y1 x2. And also, so after I'm going to take the common terms out, comparing these two and these two. Here x1 can be taken out, so actually the left hand side is z1 z2 complete bar. So over here it's x1 can be taken out, x1 x2 minus iy2 and also these two we can take minus I out, no sorry, minus iy1 minus iy1 out, then it will be x2 minus, yes, minus iy2. So these two brackets are same, x1 minus iy1, x2 minus iy2. So what is this? This is the conjugate. This is the conjugate of z1 and the z2. So it is x1 x2 whole thing bar. So this is the third theorem. Okay, fourth theorem, we had z1 over z2, z1 over z2 whole thing bar. It's individually equal to the z1 and z2 bars. So the same thing with the third theorem. So I'm starting from left hand side, and z1 over z2, I think we might have done it. Only z1 over z2 we operate it. So I'm directly using the answer of the previous result. Also you can see the answer, the result of the that simplification. We have done it the previous tutorial, so I'm directly using it. So this is the z1 over z2, the final answer, the simplification final answer. So we have to simplify it further because we have a conjugate sign. So then, so to remove the conjugate sign, so I'm writing here, it will be x1 x2 plus y1 y2 over x2 square y2 square minus I x2 y1 x1 y2 x2 square y2 square. So over here, so you can see again the denominators are same. So again I am removing this plus sign and I am just putting minus I square. Minus I square. So it will be then x1 x2 minus I square y1 y2 minus I x2 y1 x1 y2, and also the denominator is x2 square y2 square. Right, so I'm going to solve the bracket. So the bracket, when I am solving the bracket, so it will be minus I, and also here plus I when I solve the bracket. So here you can see, you can take over here x2 can be taken out, x2 then x1 minus I y1, these two comparing, again minus I y2 can be taken out, I y2 taken out, and it minus I y2 minus I y2, and it no, I'm just taking only plus. plus because here plus I by 2 out, then it's x1 minus I by 1. So you can see here that these two brackets will be same, otherwise it will not. That's why I am taking plus I by 2. So x2 square y2 square means simply x2 plus I by 2 and x2 minus I by 2. No? So these two will be same, x2 I by 2, x1 I by 1 and x2 plus I by 2, x2 minus I. You can see it's coming x1 minus I by 1, x2 minus I by, sorry, it's I by 2. So this is, what is this? This is z1 bar, this is z2 bar. So it's proved. The fourth theorem method. Actually seems a little bit different, that's why, but it's not hard, you can try yourself. And but the other important thing is, so the property that I have directly used from the tutorial number 1, you can't write it directly, you have to simplify it, you have to show it. Okay, next move to the next theorem, fifth theorem, which is z and z bar product is always greater than or equal to 0. So z mean our x plus iy, they given it, and the left hand side, which is x plus iy, so it's x squared minus I squared y squared, x squared plus y squared, right? You know, whatever the value x and y, it's always greater than or equal to 0. So the only way to be 0 is both x and y are 0. Both x and y are 0 mean it will be the 0 0. So then, but there is a chance to be 0, then you have to put it can be greater than or equal 0, but z into z bar is greater than or to 0. So this is the fifth theorem. It's actually easy. Okay, let's look at an example. Z bar plus 2i z equal 12 plus 6i. Find the complex number z. Right. So before that, we have to design. We have to take z as x plus iy because they given they find the complex number z. The z is anyway it's complex number, and I'm just putting it to x plus iy, x minus iy plus 2i, x plus iy equal 12 plus 6i. This is the previous result actually, x squared plus y squared and 2ix 2i squared y equal 12 plus 6i. This is x squared y squared, 2i squared y mean minus 2y, and I 2x, this is 2 plus 6. So comparing both two, the real part and the imaginary, so these are two different complex numbers but they are equaling. So equaling means the real part and the imaginary part both should be equal. So we did this theory, x squared plus y squared minus 2y equal 12, or 2x equals 6, x will be 3. x3 mean you can put it to here, 9 plus y squared 2y equal 12, y squared 2y minus 3 equals 0. So the factors of y is minus 3 mean 3 into 1. So it's probably y minus 3n, y plus 1 equals 0. So y equal 3o, y equal minus 1. So these are the values. We have only x value but two different y values. Two different y value mean exactly we have two complex numbers, not a one complex number. So the answer is z equal x equal 3. 3 plus I3, so 3n. And z will be again 3 plus minus 1 9. These are the values of z. So therefore we have two different complex numbers which is satisfied the previous equation. Okay, let's look at another example. Find the solutions of the quadratic equations. This is row number 1, this is row number 2. First one I'm taking, I think we did this very in the first tutorial, the very first very first discussion we simplified these kind of quadratic equations. X squared minus 6x plus 10 equals 0. So we don't have factors directly, then I'm going to quadratic square plus 10 and minus 9 equals 0. All things square plus 1 equals 0. So equal minus 1. So it's minus 1 square root is directly minus 1 square root is I, but here we have plus or minus sign. X minus 3 equal plus or minus I. So x equal plus 3 plus or minus I. Can we have two answers. X equal 3 plus I or x equal 3 minus I. But you can see the one solution is the conjugate of the other solution. So it's obviously true, because in a quadratic equation we don't have real solutions. The solution will be complex numbers, complex solutions. Then those complex solutions will be, the one is conjugate of the other complex number. So you can simplify any quadratic equation which has not a real solution, then the complex roots will be a conjugate of the other. both solutions have the connection. So I will explain it again using the second row number. So I think I have noted it. So I simplified using completing square and the roots are complex. The second equation, x cube minus 1 equals 0. So it's x minus 1 x squared plus 6 plus 1 equals 0. So this is equal 0, but here this is x squared plus 6 plus 1 equals 0. I'm going to completing square it, minus 1 over 4. So into other side, x plus half square plus 3 by 4 minus 3 by 4 plus or minus root 3 over 2. So minus root 3 mean plus 3 minus 1 over 2, which is half, plus or minus I root 3 by 2. So minus half plus I root 3 by 2 or x minus half minus root 3 by I. These are the solutions of the x cube minus 1. Actually there's one more, which is x equal 1, x equal 1 also the solution. Then we had three solutions. That's when you have a cubic equation, there should be a three roots. So the one is real, other two are complex. Then that complex root has a connection. What is the connection? One is the conjugate of the other. So that is completely true. I will explain it using the standard equation again, but anyway you have to memorize it. Once we have a quadratic equation which has a complex root, those complex roots will be a conjugate, and those roots will be connected. The connection is one is a conjugate of the other. And the other important thing is, if we have if we have fifth order polynomial function, so just assume that fifth order polynomial equation, there should be 5 roots. Then that 5 roots can be all 5 are real, can be reals, and one is real and other 4 can be complex, and also 3 will be real and other 2 will be complex. So the thing is, always if any polynomial function, if it is if it has complex roots, the complex roots are coming with the complex roots are coming with 2 by 2. So always there should be 2 complex roots. So even number of complex roots should be there. If it is fifth order polynomial function, the comparison of the roots, which is again derived to the real roots, the number of real roots, number of complex roots. The comparison is all 5 will be real, it can be real, and no complex roots, and there will be how many? 3 real roots and 2 complex roots can be there, and also 1 real root and 4 complex roots can be there. Always the complex roots are even number of complex roots should be there. But if it is fourth order, then what will happen? So all can be real, 2 can be complex, and other 2 will be real, and all are complex. So you can see all the time these complex roots are even. Okay, so this is the theorem of the previous one. What is this? This is a quadratic equation, the standard quadratic equation. If it has a complex roots, find the roots. Okay, so I'm going to take a out, x squared plus b over a, and I'm going to completely square it, c over a plus minus b squared over 4a squared equals 0. This is not equal 0. X plus b over 2a square equal b square. Here I am taking 4a square to the denominator, and just removing square root, square 4ac over 4a square whole thing plus or minus, and x plus b over 2a equals, so the given, if the roots are complex, then I'm taking my here minus 1 out, minus 1, here it's 4ac minus b square over 2a. So minus 1 is square root means I, x plus b over 2a, I plus or minus 4ac minus b square over 2a. Therefore the roots are minus b over 2a plus or minus I 4ac minus b square over 2a, right? So what's this? So again you can see plus or minus. Plus or minus means only the imaginary part is getting plus or minus. So if it is positive, and the minus 1 will be the conjugate. So therefore z is the root. If z is root, the other root will be directly, other root will be z bar. So that is why I told you all the time, if z is a root, then z bar will be the other root. That is the nature, right? So if in a quadratic equation, any quadratic equation, if they given one root, you can directly write down the other root, because according to that theory, the one complex root is the conjugate of the other. So that is the theory part behind. So this is the proof, actually. This is the proof of that theory part. I'm just suggesting you to do these three equations. So simplified it and find the roots of it, right? So okay, so now I'm moving into another special identification, square root of a complex number. So I found an example. Find square root of 3 plus 4. Actually inside the square root it is a complex number, so I assume this square root answer will be another complex number. So I'm just thinking the square root of the 3 plus 4i is a plus ib, I assume. So what I'm going to do, so this is my assumption. My assumption was the square root of the complex number is another complex number. So I'm just squaring both sides, then it will be 3 plus 4y a plus ib square, a square, the product is plus 2abi plus I square b square, then it's a square minus b square 2abi 3 plus 4y. So here this is the real part, imaginary part, real part and the imaginary part. So the both sides are equal complex numbers, then 3 will be directly a square minus b square, and also 4 will be 2ab, then ab equal 2. So two simultaneous equations and two unknown terms. So we have to find AB separately. So we need AB equal a square minus b square equal 3 and AB equal 2. So a equal 2 over b. I'm just putting it here. 2 over b whole thing square minus b square equal 3. B square b to the power of 4 equal 3b square, b to the power of 4 3b square 0. Then factors will be b squared plus 4 and b squared minus 1. So b squared equal minus 3 and b squared equal plus 1. You know, so the b was at the, what is b? Because so b was taken 4 plus 3i equal a plus ib. You know, here a, b are actually real. A, b are real. I is the imaginary part, but a and b are real, right? So here this is contradiction. It can't be happen. B squared cannot be minus 4, but then b squared equal 1 mean b equal plus or minus 1. So b equal plus or minus mean a will be plus or minus 2, right? So therefore 3 plus 4 plus 3i, which has plus or minus a plus ib, and 2 plus I1. So what is the conclusion? The square root of any complex number is another 2 complex numbers. That's the behind scene. Square root of the complex number is another 2 complex numbers. Okay, as a homework you can find this square root minus 80 minus 18i, right? So you can do it as a homework. So what is the only thing, you have to equal it to the a plus ib or something like that, and the square both side and take a 2 different equations in terms of a and b and solve that. Then you will find a and b.